Hello everybody, my name is Alireza and I'm a PhD student in Technical University of Denmark. The title of my presentation is Prediction and Optimization of Flash Defect in Plastic Injection Molding using Machine Learning Methods and Process Simulation. Here are the contents of my presentation. First I will talk about the background, then I will go for methods, then we will discuss about results, and we will have conclusions, and I will give some suggestions about future work. First, background. As you might know, plastic injection molding is one of the most important manufacturing methods for mass production of plastic parts, with a very big market share of almost 33%. And it has very considerable manufacturing advantages, including high repeatability and relatively short cycle time and net shape. But same as many other manufacturing methods, these manufacturing methods can also have many problems, including injection defects. As you can see here in this picture, we can see many defects here, including flash defect, sink marks, air traps, and weld lines. And there are many different factors that can be influential on these defects. So if you want to have a defectless product, or if you want to decrease the defects as much as possible, it's necessary to have control on the manufacturing inputs that we have. For example, I divided the parameters that can be effective on product defects to part or mold design, material, and process setting. There are several different parameters based on each of these sections that can be effective on defect formation. So, specifically in this presentation, I want to talk about blush defect. As you can see here, blush defect usually appears in shape of white hollows, usually around the gate location, or the areas that the thickness of the part dramatically decreases. So it can cause rejection of the product in standard tests. The main part that we worked on during this study is this part called bushing, and the size of this part is 63 millimeters diameter. And here you can see a sample of blush defect after doing thermal test. And here you can see the lamination of polymer, which can cause rejection of the part in standard tests. So the part we were working on was made of PVC, and it had two cavity mold with cold runner. So here are some other pictures of the same part. You can see that the blush defect occurred in almost all of them. So it seems to be very necessary to conduct a study on blush defect. Now I want to talk about the method that we adopted during that study. In this slide, you can see PVT and viscosity curve of the polymer we worked with. And these data, these graphs are based on the mold flow library. We didn't do the measurements of PVT and viscosity ourselves. So we relied on database of mold flow. And we considered 8 different input factors to be studied to see the effect of each of these factors on blush defect, and also to see if they are effective on blush defect or not. The factors are injection rate, holding pressure, melt temperature, mold temperature, runner diameter, gate diameter, included angle, and gate angle. So some of them might be effective, some of them might not. So let's see. In this flowchart, I want to briefly talk about the whole method that we adopted. First, we started with modeling. We created a CAD model, we recreated the CAD model because the factory didn't have the CAD model of the main part that we wanted to study. So based on the 2D drawings of the mold, we tried to recreate the CAD model of the part. Then we initialized finite element analysis based on the requirements of the study. And then we did the first step of design of experiments, which basically was the screening step of design of experiment. We have 8 factors, and if we want to consider many levels for each of these factors to see the effect of each of them on the output, the number of tests will increase dramatically. So first we decided to decrease the number of factors that we have by deleting some of them which are not really influential on flash defect. So we did the first step of design of experiment, which was a fractional factorial design of experiment with 2 levels only for each parameter. Then we validated our simulations using some experimental tests to see if our simulations were good. Then we conducted analysis of variances on the results of the simulations we did. Then we went for second step of design of experiment. In this step, we deleted some of the input factors that were not really influential on the outputs. So we did CCD design of experiments, this time with 5 levels for each factor, so that we can have a better resolution of the manner of effect of each factor on the results. So we conducted some new simulations based on the test suggested by CCD, and then we realized that yes, these factors are really effective, and this factor is more effective than the other one. So after all, we did some optimizations on the input factors. For example, if melt temperature is really effective, what amount of melt temperature can be adopted so that we can have least flash defect. Then in the next step, after doing statistical analysis here, we used artificial neural networks to create a predictive model for to predict the amount of blush defect based on the inputs. So we used different kinds of artificial neural networks to see which one works better. And then in the final steps, we adopted genetic algorithm to optimize the levels of those influential factors. Yes, here I want to talk about the details of design of experiment that we did. The first one was 1 divided by 8 fractional factorial design of experiments with each factors and 2 levels for each factor. So in total we had 32 tests which we simulated. Then we went for CCD, central composite design of experiment, and we had 5 levels for each parameters. So in total we did 31 more simulations. In this slide, I want to show you the CAD model that we created for the part. Yes, here you can see the 2D drawings of the cavities that I told you, and we recreated the CAD model here based on these 2D drawings. Then we went for meshing of the part in MoldFlow software, so we imported the CAD model into MoldFlow. Then we meshed the part. As you can see, we have finer mesh here in the area around the gate location because it's more sensitive, so we need finer mesh in this area, and we use coarser mesh for the rest of the part because it's not as important as the area around the gate location. This will help us to speed up the simulations. So we did so. And here you can see the mold block and cooling channels, runner system, and gates created in MoldFlow. The size of the mesh here around the gate location was 2 millimeters, while for the rest of the area was 3.5 millimeters. Now I want to briefly talk about some of the results. Yes, in this picture you can see the result of the simple simulations we did. In this area you can see a hollow area which indicates blush defect. Basically, blush defect occurs when the shear rate of the material exceeds the maximum allowable rate provided by material supplier. For example, for the PVC material we used, this amount is 0.2 megapascal. So if the material shear rate exceeds this amount, we can see blush defect in this area. which you can see a void here. But for clarity, I made this area red so that to avoid confusion. So basically, this area is where the blush defect occurs. And how we measured blush defect? In experimental tests, we can simply measure the dimensions of blush defect and calculate the area, because the shape of blush defect is almost an ellipse. So we can use the equation for calculation of the area of the ellipse to calculate the area of blush defect. But in simulations, we need to measure two lengths. The first one is the width of blush defect, and the next one is these lengths. So we used some equations to calculate these lengths based on having these two upper and bottom edges of the blush defect. So in this way, we will have these lengths and these lengths, which will help us to calculate the area of blush defect. So we can compare the results of simulation with those of experiments. And here you can see a simulation made by exactly the same inputs as this experimental part. And as you can see, both the shape and area of blush defect in simulation is very similar to those of the experimental part. So this is how we validated our simulations. And in this table, you can see the two levels for each of those 8 factors that I told you, which we adopted during first design of experiment with it. For example, for flow rate, first we considered 15 cubic centimeter per second, and the next level, the higher bound, was 25. And the same for all those 8 factors. By realizing that these 4 factors are not really influential on blush defect, we will continue only with these 4 factors. So in this way, we can design a second design of experiment, which is CCD, with more levels for each of these 3 factors. Considering more levels for each factor can help us to better realize how each of these factors can affect the blush. I will show you a diagram in next slides. Yes, and as a result of statistical analysis that we did, we get these equations, this prediction equation, which can help us to predict the area of blush defect without doing a simulation. It's not that accurate. The accuracy of this equation is almost 75–80%. It's not that accurate, but still good. A is melt temperature, B is B is injection rate, C is holding pressure, and D is runner diameter. So if we replace these letters with those amounts that we want, we can get the area of blush defect. And here you can see the manner of effect of each of those 4 influential factors on the area of blush defect. For example, if we increase the flow rate, the area of blush defect will increase. If we increase melt temperature, the area of blush defect first starts to increase slightly, then dramatically decreases. And the same for the other 2 factors. For the next step, as I told you, we decided to employ artificial neural networks to provide a better predictive model for the area of blush defect. For this purpose, we decided to have 3 different types of artificial neural networks. The first one was the basic artificial neural networks, the multi-layer perceptron artificial neural network, which uses gradient descent method to optimize the weights and biases of the links between neurons. The next one was ANN plus genetic algorithm, which replaces the gradient descent method with genetic algorithm. The block of artificial neural network is the same. The only thing which changes is replacing gradient descent with genetic algorithm. And also the same for particle swarm optimization. So in the third one, we replaced gradient descent with particle swarm optimization. In this way, we can have different predictions based on different artificial neural networks to see which one works better, which one can provide us a better predictive algorithm. Here you can see the result. Please accept my apology. This column is wrong. It's accuracy of training data set. It should be test data set, sorry. But the results are the same as test data set. For example, for basic artificial neural network, we designed 4 different setups. For example, in the first one, we considered 4 neurons in hidden layer, then 6 neurons for hidden layer, then 8 and 10. So we have 4 different setups for each of these types of artificial neural network. And finally, we realized that the one in row 3 works better because it gives us better prediction accuracy in a lower time. So we decided to continue with this one. And here you can see the training, validation, and test prediction accuracy of that basic artificial neural network. For example, for test data set, it presents almost 95% of accuracy. Then we went for process optimization. The first process optimization we did was based on analysis of variance. So if we go to optimization tab of each of the softwares of JMP or Minitab or whatever, they can give us the optimal level for each of input factors that we have, so that the result decreases or increases to a maximum or minimum point. And doing that, we saw that the area of blush defect with those levels suggested by Minitab, the area of blush defect will decrease by 74%. The initial area manufactured by the company was this one, and after doing the optimization, it decreased to almost 500 square millimeters. So it's a huge decrease. Then we decided to do the same thing using genetic algorithm. And here you can see the specifications of genetic algorithm we adopted. And after doing genetic algorithm optimization, the area of blush defect decreased by 87%, which is a considerable amount. And here you can see the process parameter levels. The initial one, this row presents the initial parameter levels used by the company to manufacture the initial part. Then we did optimizations based on statistical method, and here are the levels of each factor suggested by Minitab. And here you can see the levels of each factor suggested by genetic algorithm. And the last column is the area of blush defect after employing these parameter levels. And here you can see the initial part manufactured by the company. I put some effect on the picture to see, so that you can see the area of blush defect here. I don't know if you can see the area of blush defect here. And here is the simulation made exactly with the same inputs. And yeah, you can see that the area and shape of blush defect is almost the same. And after doing genetic algorithm optimization, you can see that the area of blush defect, both in experimentally manufactured part and simulation, decreased very much. In summary and conclusion, I want to summarize what I said. The main reason of blush defect was too high shear rate in material, and we considered a factor to be a study to see which one is effective. Then we created a digital twin of the process. Then We did design of experiments to avoid doing this excessive number of tests. Then the results showed us that the runner diameter, holding pressure, melt temperature, injection rate are really influential on blush defect. Then we did two types of prediction models. First, based on analysis of variances, and the next one based on artificial neural network. We realized that artificial neural networks with accuracy of 95.2% prediction accuracy works better. Then we implemented genetic algorithms on the process parameters, and we realized that the area of blush defect in this way can be decreased by 87%. And some suggestions for future work. For example, we can extend the database of injection molding with different materials. This study was done only with PVC, but if we can have various materials, maybe POM, polycarbonate, or whatever, if we can extend the database that we have, we can extend this study and we can make more accurate predictions also with other materials. And yes, the next suggestion is that using reinforcement learning to evaluate prediction accuracy for the part with various sizes. For example, if we are simulating a Lego part, it can be manufactured in different sizes. So we can use data from previous studies also for the new studies. In this way, we can need only fewer amount of data for the new study. And also we can include the temperature gradient of the melt flow in the simulations. Because in the blush defect, the melt temperature is really important because it has a really considerable effect on the viscosity of material and as a consequence on the shear rate. If we can have the gradient of the temperature in the cross-section of the material going to cavities, we can have more accurate simulations. And also we can use white box algorithms like logistic regressions or decision trees to figure out the manner and the extent of effect of each parameter on blush defect. Thank you very much. This project is supported by DIGIMAN project, and also I would like to thank supervisors team, especially Guido. Thank you very much, and thanks for your attention.
Thank you, Alireza.